In this video, we are going to discuss matrices, SAQs. Question is page number 71, example 4. Very important. Many times repeated in the examination also. If matrix A is equal to cos theta, sin theta, minus sin theta, cos theta, then show that for all positive integers n, a to the power of n is equal to cos n theta, sin n theta, minus sin n theta, cos n theta. See, we can prove these type of problems in the matrices by using the mathematical induction. See, we know that mathematical induction we can prove by using the 3 steps. See, in the solution, first what we have to take? First you have to take that given matrix. So given that matrix A is equal to cos theta, sin theta, minus sin theta, cos theta. See, this is a 2 by 2 matrix, right? So now again what you have to do? So this can be proved, I already told you, by using the mathematical induction. So what you have to do now, first let S of n be the statement. S of n be the statement. S of n be the statement that. What is the statement? So here the matrix A power n is equal to cos n theta, sin n theta, minus sin n theta, cos n theta. This is the S of n. So A power n is equal to matrix cos n theta, sin n theta, minus sin n theta, minus sin n theta, cos n theta here. So this is S of n. Now I already told you it is we can prove by using the mathematical induction. So in the mathematical induction, now I am taking step 1. So step 1. In the step 1, what we do? So put n is equal to 1. So where you have to put n is equal to 1? In the S of n. So what is S of n here? A power n. So now S of 1 is equal to a to the power of 1 is equal to, in the a power n matrix, n replaced by 1, cos 1 into theta, sin 1 into theta, minus sin 1 into theta, again cos 1 into theta. N is replaced by theta. So now what happens here? So if you observe that we get this is the same matrix. A is equal to, so cos theta, sin theta, minus sin theta, cos theta. See, we get the same matrix only here, matrix A. So that's why in the statement, so in the step 1, after taking the n is equal to 1, we get the same matrix. Now we can say that, so S of 1 is true. So it means that the given statement is also true for n is equal to 1. The statement is true for n is equal to 1. Now in the step 2, what we have to do? In the step 2, we have to assume that the statement, that is S of n, is true for some n is equal to k. But what is k here? N is equal to k. K belongs to the integers. K belongs to positive integers here. K belongs to z plus. Z plus represents the positive integers. So what we have to do now in the step 2? So the meaning of this is S of k is equal to the matrix A to the power of k is equal to. The matrix A to the power of k is equal to. So replace n by k in the A to the power of n matrix. So now cos k theta, sin k theta, minus sin k theta, so cos k theta. Now actually we assumed that the statement is true for n is equal to k also. Then finally in the step 3, So in the step 3, what we have to prove that? We have to prove that the statement S of n is also true for n is equal to k plus 1. See, what is the mathematical induction says that the given statement is, we have to prove that in the step 1 it is true for n is equal to 1. In the step 2 we have to assume that the statement is true for n is equal to k, and in the step 3 we have to prove that the same statement S of n is also true for n is equal to k plus 1. Prove that in the step 3 the statement is also true for n is equal to k plus 1. Now you consider a to the power of k plus 1. See, a to the power of k plus 1 is equal to, we can write it as a to the power of k into a to the power of 1. See, a to the power of k plus 1 we can write it as, like we have the property a to the power of m plus n, so which is equal to, can be written as a to the power of m into a to the power of n. So as per that property we can write it as a to the power of k plus 1 is equal to a to the power of k into a to the power of 1. See here, which is equal to a to the power of k, we have the matrix A, and a to the power of 1 is also the matrix A. So both we have to multiply here. So which is equal to, we have the a to the power of k matrix is cos k theta sin k theta. Already we considered in the step 2. So this is minus sin k theta cos k theta, we have a to the power of k matrix into the matrix A is, we have cos theta sin theta minus sin theta here in the second row. So cos theta. So we have to multiply both the matrices to prove that the statement is also true for n is equal to k plus 1. Now which is equal to here. So this is multiplying. See, observe here, first row, first column multiplying. Both are 2 by 2 matrices only. Number of columns in the first matrix is equal to the number of rows in the second matrix. Resultant matrix order is also, we get 2 by 2. So that's why here multiplying first row, first column. So cos k theta into first column in the second matrix cos theta, and immediately put the sign plus sin k theta here. Sin k theta into, this is minus sin theta. Again same first row, second column multiplying in the next matrix. See, we get here cos k theta into, in the second column we have sin theta, and immediately you keep the sign plus. So sin k theta into, so here we have cos theta. Similarly, now multiply the second row, first column. Second row in the first matrix. So first column in the second matrix, this is minus sin k theta into cos theta. So plus immediately, and cos k theta here, cos k theta into minus sin theta. So now second row, second column in the next matrix, minus sin k theta into sin theta plus cos k theta into cos theta. See, now we get like this one. So what I am doing is here, so removing the brackets, multiplying, this is cos k theta into cos theta into cos theta, and here plus into minus is minus sin k theta into sin theta, and here we get cos k theta into sin theta, cos k theta into sin theta, and plus sin k theta into cos theta, and here we get, both are the minus only here minus also there, here also minus is there. So taking minus common, then here writing it, this is first cos k theta cos k theta into sin theta, and it becomes also plus sin k theta into cos theta. And here this positive term first writing here, cos k theta into cos theta into cos theta minus sin k theta into sin theta. See, observe here. So we have two formulas exist here. So suppose if you take cos theta, cos k theta is A and theta is B. So we get here this in this matrix. So first row, first column, in the second row, last element, both exists the same formula only. That is, we have here cos A plus B. That means cos A cos B minus sin A sin B, which is equal to, we have the cos of A plus B, we have formula, and here first row second element, and in the second row first element. So for both exists the same formula. That is, if you take the cos k theta is A and theta is B, here this is A and this is B, we get sin A here, sin A cos B, and plus cos A sin B, we get cos A sin B, which is equal to, so this is sin of A plus B. This is sin of A plus B. So that's why which is equal to, we get here. So cos A cos B minus sin A sin B, we get cos of A plus B, that is cos k theta plus theta. And here also sin A, k theta is A and theta is B here. So that's why this is sin A cos B plus cos A sin B, we get sin of A plus B, that is k theta plus theta. Again here minus, as it is minus of A. So we get here cos A, otherwise sin A cos B plus cos A sin B here. Sin A cos B plus cos A sin B. We can write it as sin of A plus B, that is sin of k theta plus theta. And here when you take cos theta is A and theta is B, here cos A cos B minus sin A sin B, we get cos of A plus B, that is cos of k theta plus theta. Further it is now in the S of k plus 1, that is we consider A power k plus 1. After taking the theta common, we have k theta plus theta. If you take the theta common in all the elements, so we get cos of k plus 1 into theta, sin of k plus 1 into theta, and minus sin of k plus 1 into theta. So cos of k plus 1 into theta. See, observe that wherever k is there or wherever n is there, we get that k plus 1. So therefore, after getting like this, we can write that the statement is true for n is equal to k plus 1 also. It is also simply can be written as s of k plus 1 is also true. S of k plus 1 is also true. So therefore, finally we can write that by the principle of finite mathematical induction. So S of n, the given statement S of n is true for all positive integers, n. See, so like this we can hence prove. So that's why the given problem we can prove that by using the mathematical induction by using 3 steps. That is, in the first step 1 we have to prove that the statement is true for n is equal to 1, and in the step 2 we have to prove that we have to assume that the statement is true for n is equal to k, and in the step 3 so we have to prove that the same statement is true for n is equal to k plus 1 also. So we prove like this. So that's why the given problem we can prove by using the mathematical induction.